Everybody knows the three-dimensional sphere. Today I will show you how we can generalize this concept to n dimensions. The sphere in 3 dimensions is defined by the Euclidean norm of the vector x, y, z. This means we take x squared plus y squared plus z squared, and it has to be smaller or equal to r squared. We can apply the same concept with the Euclidean norm to different dimensions. If we're 2 dimensions, we just neglect the z component, and in 1 dimension, we just neglect supplementary the y component. We can generalize this concept of sphere easily to n dimensions, where we just take the sum over all components cubed, and it has to be smaller than the radius r squared. But what is the volume and the surface of these objects? If we look at 3 dimensions, it's very obvious. Everybody knows this formula: 4p over 3 times r cubed. How can we obtain this formula? We just do a multi-dimensional integration in spherical coordinates. We can also identify that this term here is just the surface of the 3-dimensional sphere, and we do an integration from 0 to r over it. In 2 dimensions, the generalized volume is just the area, and like in 3 dimensions, we do the same. We do an integral from 0 to r over the 1-dimensional surface, which is just the circumference of the circle. In 1 dimension, it's trivial. It's just a line with the length 2r. Now we want to know what's the volume and the surface in n dimensions. The expected result of the volume of the n sphere has to be in the form alpha n, which is some kind of constant depending on the dimension and independent of r to the power n. We can use the fundamental theorem of calculus to write the volume in the integral form, and this part is just the derivative in terms of r. And if we compare this integral to our previous integral in 3 dimensions, 2 dimensions, we know that this part has to be the n minus 1 dimensional surface. So if we want to know the volume, we just have to know the n dimensional surface. We have to find the general formula. And if we try to do it, we do an integral over all the solid angles of the basic integration volume. But for the general case, for n-dimensional spherical coordinates, this integral is really cumbersome to calculate. So we cannot do it in a general case. So we need some kind of trick, some kind of answer to solve this problem. And we can use the Gauss integral. We will calculate it 1 time in Cartesian and 1 time in spherical coordinates. The first integral we calculate is the classical Gauss integral in Cartesian coordinates, but this time in n dimensions. So instead of a scalar, we have a vector here. Using Fubini's theorem, we can split our integral in separate integrations over x1 to xn. If you watch my previous integral, you directly know that the integration of the Gauss integral from minus infinity to plus infinity equals square root pi. And we have n integrals, so our end result is pi to the power of n halves. Regarding the integration in spherical coordinates, we have an integral from 0 to plus infinity over the radial component r, and then we have an integration over the solid angle. Our function does not depend on the solid angle, so we can directly write the integration over the solid angle in the forms of the n minus 1 dimensional surface, which we can write as n times alpha n times r to the power of n minus 1, which we have proven here. So we do a smart change of variables where we exchange r squared with t, and we change dr to dt. This is done. Dr equals 1 over 2 square root t times dt. If we combine everything, we get n here and alpha n, and we put it here. We also take the factor half from here. We take the factor r to the power of n minus 1 and exchange it to t n to the power n minus 1 over 2. And you also take into account this factor, which is t to the power of minus 1 half. Combined, it's t to the power of n half minus 1. And if we look at this integral, we know that this is the definition of the Euler gamma function. So let's put everything together. So I1 equals A2, so p to the power of n half equals alpha n times n halves times the Euler gamma function. And in a previous video about the Euler gamma function, I have proven that n, or generally z, times gamma of z equals gamma of z plus 1. So now we can write an alpha n directly. This will result in alpha n equals pi to the power of n halves over gamma function of n halves plus 1. Okay, let's summarize what we found out. So our factor alpha n equals pi to the power of n halves over the gamma function of n halves plus 1. So we can now determine the volume of an n sphere using this formula. And if we do the derivative of this formula in terms of r, we can also get the volume of the n minus 1 dimensional surface. And I did it here, I did the derivative here, and I also add these supplementary 2 times here, which cancel each other. But we can use the property of the gamma function and pull out the n halves here, which will cancel with this n half. So in the end, we end up with this term. Finally, we found out a formula for the general n sphere and its surface. But why are we even interested in n-dimensional shapes? In the normal life, we work most time with 3 dimensions. But in physics, we also work with the concept called phase space, which is a combination of the position and the momentum of all particles in a system. And if we have just 2 particles in 1 dimension, we already have 4 dimensions, so 2 times the position, 2 times the momentum. And 1 coordinate is describing exactly the state of a system. And a sphere is just one of the most basic concepts you can have. So it's common to appear in phase space. So it's good to have a general formula. Even though it's a bit complicated, we can generalize it. Amazing. Till the next time.